Hi, this is Terry Iverson from Champion Now and CNC Rocks. We're going to talk in this program about CNC turning, and before we do that, we want to talk about manual turning on a manual lathe. Going back into the 60s, the 1960s and back, a lot of the turning in this country was done in a manual fashion. So the skill set of the operators was very high, and they were able to make the most complex components on a manual lathe. This particular lathe used to be made in the United States and now is no longer. We actually rebuild some of the original lathes of this type, but they're also made overseas just because they're not made in this country anymore. But when you get into precision work, R&D, which is research and development, prototype, which means one of a kind, 1, 2, 3, low volume. This type of lathe is used in a lot of tool rooms, a lot of precision machining, machine shops, and a lot of tool and die type work, in addition to research universities and the likes of. So this is the headstock on a lathe, on a CNC lathe or a manual lathe, but this is the headstock where the spindle resides. The spindle is inside, has very precise bearings that support the spindle and make it very rigid and accurate. And it has a belt that wraps around a pulley that goes down below here on a motor. And as the motor spins, the belt transfers the motion up to the pulley. The pulley's connected to the spindle, and as a result, it spins. This particular machine has a variable speed inverter. So with this rheostat, I can change the RPM. And you can see right now I'm at 1900 thereabouts revolutions per minute. And I can go all the way down. This machine will go up to 4,000 RPMs. And so what you want to do on a lathe is you want to spin presumably round bar stock and then machine something. In this particular case, this is a Christmas tree. This is the time of year where Christmas is next month. So one of the first parts I was taught to make on a lathe was a Christmas tree. And the Christmas tree would be out of round brass bar stock. And what you would use is you would use a turning tool, and you would, on your carriage, you would have your power feed alternated. This allows you to feed the carriage and the cross slide. This is the carriage. This is the cross slide. This is diameter. We'll talk about diameter and length. Length is carriage related, and diameter is cross slide related. And what these levers do is they allow you to power feed without manually feeding, so that you have a feed rate, in other words, rate of feed that the tool is going on the part, and you can alternate, have the Z, the length, while you alternate the diameter. And what that does, it gives you a really nice stepping motion that allows you to create on a 45 or 60 degree angle a Christmas tree. And so consequently, this just gives you one idea of what a lathe can do. We'll talk about, when we go to CNC, a lot of other different types of parts and how you can recognize parts in your daily life. But this is the first type of part that I learned on a lathe. It's totally decorative. There's really no useful functionality of this part, but it at least gives you some idea of length, diameter, and alternating such as you turn a taper. And then, of course, you can cut off, and then you have the base. This would be a grooving operation, so you'd use a grooving tool to groove to the base of the tree. So back to the lathe. We have the machine rotating, the spindle rotating. We have a piece of an arbor in it. We'd normally have a piece of stock. And then this particular machine has both inch and metric dials. Different parts of the world, when I was a youngster in grade school, they used to tell us that we had to learn metric. And so, being a good student, all of us tried to learn the metric system. Well, that was a long time ago. That was in the portions of the 60s and the 70s. For some reason, we're more accepting of the metric units, but we haven't quite gotten away from the inch units. And so many of us in the industry, we convert to metric, or we get accustomed to a certain facet of the metric system, but not entirely leaving the inch behind. So you'll see on a machine like this, they'll have dual dials. We'll have inch. In this particular case on the carriage, we have 10,000ths per increment, and we have 0.2 millimeter per increment on our carriage, and we have 1,000th of an inch on our cross slide, and then 0.02 millimeter on our cross slide in metric. So basically, you can position your tool would sit on the tool post. Once again, a lot of the concepts that we talk about in manufacturing and machining are very literal. Cross slide goes across, tool post is where the tool actually resides, the cutting tool. The tool post many times will sit on an angle so you can retract your tool during threading operations. Let's talk about threading. Over here, on the far end of our machine, you'll see a gearbox. And the gearbox is set up so you can do both inch and metric threading. Not all gearboxes are set up, some are just set up for inch. So you'll choose what thread you want, what pitch you want to run or cut, and then what you'll do is you'll engage a half nut. And the half nut is a clamshell, usually a bronze type of material that allows you to open and close on a lead screw. And a lead screw is inside of this enclosure. So the lead screw has a certain pitch. It's an Acme thread, and some of these terms may or may not make sense to you, but the clamshell clamps down on the lead screw so that the carriage moves in conjunction with the lead screw. Once you have the clamshell, or the half nut, I should say, clamped on the lead screw, then this carriage will move in conjunction, in unison, with the gearbox. And once your gearbox is set for a certain inch or metric thread, which you control in this area, then when you engage the spindle rotates at a certain RPM, and the lead screw correspondingly rotates as well. Once this is engaged, and you actually engage your feed, which is up on this lever, then it'll actually move along in such a fashion to cut a certain pitch thread that you've actually set in the gearbox. When you get to the end, there's a little set screw and a little stop on this rod. And what this rod does is it actuates and activates and stops the actual threading motion of the gearbox. And so what you'll do is this lever here will retract from the part that you're cutting the thread, so you can then feed back to a point in front of the part with this stop. So these two stops are in front of the part and at the end of your thread. So when you come along, this will start threading, not manually, by the way. It'll be moving in conjunction with the spindle. Probably won't be threading at 1700 RPM. You'll probably be at 750 or 1000, somewhere in there. And then this will move in such a fashion to the point where it hits this stop block over on my left hand, and once it does, it kicks this out. Then you can retract your tool, which once again, this is usually on a 45. You retract your tool, you kick it back the other way, and it feeds back until it hits this, which is in the beginning of the part. Once it hits this, then it'll kick this into neutral. You can put your tool back in and dial however many thousandths or fractions or decimals of metric, millimeters, your next pass is, and then you'll kick this so that it'll then do your second pass. Later in our film, what I'll try to do is make sure we cut a thread so I can demonstrate that more readily and more succinctly so you can get the concept more than what I can show right now. So that gives you a little bit about an idea of what a manual lathe is, what a manual lathe can do. Many times, if people in prototype shops want to do a taper, on the back side, you can actually have a taper attachment. And this taper attachment can be set for an angle. So what it'll do, it disengages with the carriage and engages back on the back side. So whatever angle you have that set at, it'll follow that angle. So if you want a 60-degree angle or a 45-degree angle or a 30-degree angle, you can do a turn along the length using a taper attachment. Once we go to CNC, everything's computerized, and merely with the G-code or a CAN cycle or with 2 points, it can interpolate a certain angle or a certain taper. Over here we have the tailstock. When you have long components that need to be supported, one of the mechanical principles of turning is that if your part's 1 inch in diameter, if this is approximately 1 inch in diameter, without support, you can't really turn longer than 3 inches long. There's that 3-to-1 ratio. So if you want to do something 10 inches long with a 1 inch diameter, you're going to be 10 times diameter. They call that length to diameter ratio. Sometimes people use the initials LD or something of that nature. So when you do that, you'll have a tailstock center, which is conveniently located in the center of the tailstock and on center line of the spindle. And the end of the part will have a center drill or a center that a center drill has put into the part. And this center, live center, because it rotates, will come into the end and support a part. And when you support a part like that, many times they call that between centers. Even though one side may be in a collet, and the collet is the device that holds the part. Right here we have a arbor that's part of the collet, so the collet's built into the arbor. But sometimes you'll have a center here and a center here, and that would be truly between centers. Hopefully in our inspection segment, I'll have something between centers that I can demonstrate that. The other thing on a tailstock that you would use, and you could move the tailstock with this handle here, both in and out. And you can also move the body of the tailstock closer or further away for shorter or longer parts. But you could also put a drill chuck in here, so if you want to drill into the end of a part accurately, very accurately, and very in a controlled fashion, you can put a drill chuck and then put a drill bit in the drill chuck and drill a hole into the end of the part. Some of the other concepts about this particular lathe is that this is called a dovetail bed plate. It's one of the principles of accuracy and rigidity that maintains this machine to be a very rigid and very accurate manual lathe. The reason it's called dovetail is if you look from the end, it'll look like this, where you have an angle on this side and an angle on this side, and it actually looks like the end of a dovetail. This is usually hardened and ground, and it's very not only accurate, but very long-lasting, so that as it wears. This rack is what is engaging for you to actually move the actual carriage, and there's a mating gear inside that correlates to this particular handle, and that gear travels up and down this rack. That's where they get the term rack and gear. On the cross slide and on the tool post, you'll have a lead screw that goes down the middle, and then you'll have a corresponding nut that have to be very accurate to each other. In fact, the nut has to be drilled in place and tapped in place after it's already mounted into the tool post and after it's already mounted into the cross slide. And then the feed screw goes in. There's a bearing on the end where the dial is located, and same thing with the tool post. to make sure that it's very accurately held and in the motion of actuating both in and out the cross slide and in and out the tool post, and of course as well as the carriage. All these things are very accurately transfer the motion very accurately and very smooth. One last concept is that in order to make these lathes accurate and straight, there's such a thing called a gib. And a gib is a piece of metal that is many times tapered, and it goes along the surface in here. It's cut, in this particular one, it's covered up. And so what you do is we do something called scraping, which is a manual operation. It's almost like a flaking operation to make it very, very straight. And then as you wear, because it's tapered, as the bed plate wears over time, you will adjust the gib. And you'll advance the gib because it is tapered in a fashion that it'll get into an area that it hasn't been worn and kind of moves it along into a nice, freshly scraped, straight surface. So you'll have gib on the carriage, you'll have a gib on the cross slide, and then you have a gib also on the tool post. On the tailstock, you'll have a gib, and that'll be scraped, but the tailstock only moves to position, so you really don't have a means or a need to scrape that gib all that often. As things wear, many times we try to scrape the tailstock when we rebuild these machines a tenth or two high, because as you run a lathe and you run a spindle for over a period of time, it actually grows. There's a concept called thermal expansion and thermal growth, and that has to do with the coefficient of expansion of different materials. This is like cast iron, which is usually very thermally stable but still does grow. And so this, in essence, as you use it, will rise ever so slightly, maybe just 1/10,000th of an inch or 2/10,000ths of an inch. So you want this to be at that height, the center, the tailstock center, or the live center. So you'll try to adjust them so that this is slightly higher, ever so slightly, than the headstock. All right, so on a manual lathe, you have a power feed module. This motor feeds both the carriage and the cross slide in an automated fashion. So if you were manually to spin either the cross feed or the cross slide and the longitudinal carriage feed, your finish on your part wouldn't be very smooth. And if your finish isn't smooth, then most likely your tolerance won't be accurate either. So when the spindle's running, and right now we're at about 1172 RPMs, you can turn on the power feed, and this resistor says carriage feed. In actuality, it does carriage and cross slide. And these levers right here, if you lift this lever, you can see that the carriage only right now is feeding, and that I have control over it fast and slow. And then if I want to stop, I disengage the power feed. The second feed, the second knob, is for the cross slide. And you can go different directions. I was coming out, which is away from my diameter. Now I'm going in. So if I was doing a facing move, I can do it fast or I can do it slow. Now there's an interesting concept here that I'll talk about. When you're doing a facing move on a lathe, the smaller the diameter, usually as you get closer to center, the faster the RPM would go. So you try to correlate the feed rate with the spindle speed. Well, in manual machines, you can't really do that. So you'll sacrifice surface finish and capability on a facing operation on a manual lathe. When you go to a CNC lathe, which is computer numerically controlled, they have something called constant surface footage, or constant surface speed. And so what that means is As your RPM goes up and you go closer to center on a smaller diameter, your feed rate will be consistent, and so it'll go faster. But the ratio from the spindle speed to the feed rate will be the same. Hence the term constant surface speed. So once again, this is a cross slide, and I can go either to or, closer to 0 to center line, or in this case, I'm coming away from center line. So that's a bit of an explanation, or more detailed than I initially had indicated on the power feed module on a precise manual lathe. One of the facets of a small precise lathe is that it's a collet machine. And so a 5C collet, and we'll talk about that in our work holding segment, but a 5C collet will hold a part very accurately. And what this allows you to do is this is the collet closer. Remember I said a lot of the terms in manufacturing are very literal. So the collet closer is going to close the collet. So this happens to be an arbor, but if this was my part, I would place my part inside the collet, and then I would close the collet closer. I'd close the collet with the collet closer. Now in some production machines you can have a pneumatic collet closer, a hydraulic collet closer, but on a manual machine, a lever-operated manual collet closer is perfect. So when you're running piecework, open the collet, take your part out, put your next part in, close your collet. And the collet is a draw-in style collet, which you size to the diameter of your part and the diameter of your collet as close as possible. Otherwise, you can get into some work holding issues if you don't. So those are the concepts I have on manual turning today. As we go through, that will help when we start talking about CNC turning. And hopefully I've described the manual turning process well enough so that everyone can understand and appreciate it.